Yeah, before the slides come up, let me just say that Alexander fell sick shortly before going to the airplane here, so he couldn't make it. And I'll step in and do my best to deliver the presentation to you. Of course, I'm not as much an expert as Alex would have been, and I didn't practice the timing. But let's see what we can do. At least I know about the work. Yeah. So Alex, this is a reports on work that Alex did when he visited McGill a while ago, where he was applying a self-supervised learning approach that we have established for polarized light imaging data to the hippocampus, and worked closely also with Jordan, who's also here today, and who might want to step in case of some questions as well. The idea is quite similar to a few things we have seen here. For example, what Christian has proposed, that we learn in a self-supervised fashion only by observing data how to represent textures in a latent embedding that is useful for downstream tasks. And here we are looking at polarized light imaging. We have seen quite a few of those images already with the nice fiber orientations. And the way that this works is that we have unstained tissue, which is imaged with light that goes through a polarizing filter, and by imaging it at different polarization angles, we're actually able to derive fiber orientations. From that, of course, we can talk much more about this, but it's not the main topic. The important thing is that this data is very rich and also very complex. So if we look now in that case in the hippocampus, and we look at some of the modalities that we can compute out of the polarized light in imaging data, which is here on the left, transmittance, so basically the amount of light coming through, and on the right, the derived fiber orientation maps. We can see that there's rich texture in the hippocampus, which actually allows to delineate subfields of the hippocampus. And that has been done in a publication, for example, here by Michael Zaney in 2017. But it is, of course, very time-consuming, and it requires a lot of expertise to do that. So we know this information is in the data, but it's quite hard to describe how to do it and to navigate the data if you're not an expert. So, of course, here we have a use case for feature learning to derive descriptions of the texture that are easier to process and easier to segment, for example. Yes. So what Alex has been doing is also to set up a network that works on small patches of this data, and it actually reads in the raw stacks of polarized light imaging, which is a multi-channel image, using a contrastive learning loss. And then you always have the question, is contrastive learning, which pairs of patches or input images do you present to the network that encode positive examples, which denote something that is similar, and negative ones, which encode something that should be very dissimilar. And you could, of course, do this by sampling small image patches in the same section at different distances, and by saying something that is very close should be similar, something that's far apart should be dissimilar. This is what Alex has been doing first, and what she called contrastive learning 2D. But later on, he also introduced an approach, which we report on here, which is called CL3D, where we use neighboring sections and compare patches from neighboring sections to the as positive pairs if they are close by. And this is much more powerful because as you can see, if we have a registered stack of histological sections, these patches are much closer to each other, so the information is actually better for contrastive learning. So the idea is then that you put such positive negative pairs into the system, and we use this SimClear loss function info NCE related to what Christian has presented as well, where two of these patches go into a network, and the loss tries to push similar things together and dissimilar things apart. That has been done here. And we have been looking at the resulting features. So the features in this network choice, which is a reduced ResNet architecture, have 256 channels. The patch size is 128 pixels, so it's smaller than what Christian is doing by purpose in this case. And if you look at some of these channels, of these 256 channels, you can already see interesting structures, right? So here we just chose a few of them, channel 8, channel 96, channel 191, and they delineate or they highlight different anatomically relevant aspects. Of course, this is not yet easy to navigate, right? So we are hand-picking channels here, and we find certain aspects in different channels. So we see there's something in there, but it's still hard to process and to handle. So Alex worked together then with Jordan Kraka, who is here, an expert in the hippocampus, to actually go into a canonical space in the unfolded hippocampus. So he computed the surface of the CA region and extrapolated it across missing data to actually get surfaces here for this data set. And based on these surfaces, we could use the HIP unfold framework that Jordan has already talked about and has developed to unfold the whole hippocampus voxel data into a canonical space, which can be described across, along these anatomical axes and can be nicely evaluated and compared also to data from other brains in a coherent fashion. So that has been done, and in order to derive features in that canonical space, we actually looked here at the mid-surface at depth 0.5 and extended then the mid-surface to the inner and the outer direction until we're reaching the outer and inner surface. And then along those profiles here, which is then 3D, of course, we see here a 2D section, but it's 3D, we could then retrieve these features from the contrastive learning at each point. Yeah, we did this at 17 time points, so 17 time points, so 17 different depths, and concatenated these features, which are of size 256. So what we obtained is for each surface vertex here, a feature which is more than 4,000 dimensions. And that's of course huge. So we used PCA to extract the most relevant components here. So you see here on the right a projection to the first 6 components, which carry a lot of the variance, as you can see here, and these provide meaningful shapes. You see here the component projected to the actual surface and to the unfolded surface in all these cases. The actual analysis in the paper, which we published and presented at ISPI this year, had 52 PCA components, which explain 80% of the variance. And when you then look in the unfolded space, you look at these PCA components here, again the first 6, and then we plot also the subfield delineations that we have from the atlas here. You can see that these components carry a lot of information of the subfields. So there's explicit highlighting of a couple of subfields. Sometimes we also see a mixture, but it is in part quite distinct how closely these principal components highlight the different subfields without, of course, having seen in training any subdivisions of the hippocampus. What you see here on the right, I didn't check my clock, so you have to stop me since I didn't practice the talk. I'm not sure if I'm in. Okay. So what you see here, these black delineated areas, that's where we had missing data, which was extrapolated, and in the colors you see the parcellation from the atlas, which has been transferred here. What we could of course see is that these features align well with these hippocampal subfields, and in the paper this was compared to features derived from more classical approaches, fractional anisotropy, and some other measures where we use the same approach of PCA clustering and so on, and we could see that these features, these contrastive learning features, were much more powerful, much more precise in explaining the subfields. Yeah, so by combining this approach with this HIP unfold framework in the hippocampus, we were then able to show that we can characterize the architecture quite nicely from the complex PLI data. and explain regional organization. So you could see that these features could be useful for automatic mapping and automatic identification of the subfields. And it will be very useful also for multimodal integrations and multimodal mapping. Jordan has already explained here that, that there's much more data being integrated into this canonical unfolded space with which such features can be nicely combined. Yeah, and there's another paper actually out which explains in more detail the underlying method for the contrastive learning, which has originally been developed on the Vervet brain. It's currently a preprint out. That's in submission, but if you search for Alex on arXiv, you will also find a longer paper on the methods. All right, thanks for your patience.